Hey everyone, how you guys doing today? Getting right into the video. We're starting on chapter 17. Oh, I had it open twice. Run anyway. So we gotta always run that first cell as always. Inheritance. Yeah, this one's a big one, right? And conceptually, it is about extending functionality, right? And we kind of brought this up in the previous video as well, wherein if you have a class or if you have a group of classes that are interrelated somehow, right? They have some, like in the previous chapter, we were drawing shapes, right? With the different classes. You could have, and we brought up the point of polymorphism that they all implement a draw function. What you could do is you could have a more generic class called shape, which has more generic functions that all of them need. And then each class that you inherit from shape will already have access to all those functions. So you don't need to write them again, and you can just extend their functionality, right? And that's like in terms of what you can do, but it's even broader than that, right? Inheritance can mean like inheriting properties, attributes, methods, functions, all kinds of stuff. But um, I think I think that's best if you just get into reading the chapter. So inheritance. The language feature most often associated with object-oriented programming is inheritance. It is. Inheritance is the ability to define a new class that is a modified version of an existing class. In this chapter, I demonstrate inheritance using classes that represent playing cards, decks of cards, and poker hands. If you don't play poker, don't worry. I'll tell you what you need to know. Um, there's a lot of I words here, which it's not very common. I don't see that very commonly in textbooks. But whatever. Representing cards. There are 52 playing cards in a standard deck. Each of them belongs to one of 4 suits and one of 13 ranks. The suits are spades, hearts, diamonds, and clubs. The ranks are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Depending on which game you are playing, an ace can be higher than king or lower than 2. If we want to define a new object to represent a playing card, it is obvious what the attribute should be, rank and suit. It is less obvious what type the attribute should be. One possibility is to use strings, like spade for suits and queen for ranks. A problem with this implementation is that it would not be easy to compare cards to see which had a higher rank or suit. An alternative is to use integers to encode the ranks and suits. In this context, encode means that we're going to define a mapping between numbers and suits or between numbers and ranks. This kind of encoding is not meant to be a secret. That would be encryption. Yeah. So encoding, I think in general in CS, and there's a data science concept as well that's related, is essentially just finding a different way to represent something. And usually it is about finding a numeric way to represent something non-numeric, right? Um, a, an example, a very simple example, right? If you have like a table in which there's a column gender, right? Say it's a table of customers or something like that, right? And gender can be male or female, right? Which you could shorten to M or F. But then you could also so M or F is a way to encode for male or female, right? So you could extend that even further, right? Because like I said, this is generally speaking a way of representing these kinds of things numerically. So male or female could be 0 or 1, right? Um, so yeah, so that's essentially what encoding is. Um, for example, this table shows the suits and the corresponding integer colors. So this is the suit, this is the code for the suit. With this encoding, we can compare suits by comparing their codes. To encode the ranks, we'll use the integer 2 to represent the rank, 2, 3 to represent 3, and so on up to 10. The following table shows the codes for the face cards. Jack is 11, Queen is 12, King is 13. And we can use either 1 or 14 to represent an ace, depending on whether we want it to be considered lower or higher than the other ranks. To represent these encodings, we will use two lists of strings, one with the names of the suits and the other with the names of the ranks. Here's a definition for a class that represents a playing card with these lists of strings as class variables, which are variables defined inside a class definition, but not inside a method. So yeah, that's what a class variable is. That follows around the class. So every instance of that class would have access to those variables and they would be set in the same way. Unlike a variable that is instance on the instance level, which you normally define in the dunder init function. Here's a definition of class that okay. Class card represents standard, suit names, rank names, all right. The first element of rank names is none because there is no card with rank 0. By including none as a placekeeper, we get a list with the nice property that the index 2 maps to the string 2 and so on. Class variables are associated with the class rather than an instance of the class, so we can access them like this. Card.suitNames. Right? So here you'll note, because it's a class variable, you can access it by using the class name directly rather than having to instantiate the class first. We can use suit names to look up the suit and the corresponding string. Boom, boom. And rank names to look up the rank. Jack. Card attributes. Here's a dunder init method for the card class. It takes the suit and rank as parameters and assigns them to attributes with the same names. Now we can create a card object like this. Use the new instance to access the attributes. It's also legal to use the instance to access the class variables. Yeah, so like I said, class variables can be accessed at either level. But if you use the class, it is clear that they are class variables, not attributes. Here's a dunderster method for card objects. Def dunderster rank name equals card.rank name self.rank. Suit name equals card.suit name self.suit. Return rank name of suit name. Okay. So this is the string representation of the card. It's a dunderster and basically just gets the actual rank and the actual suit from the integer encodings. So Queen of Diamonds. Following diagram with the card class object and the card instance. Card is class, so its type is queen. Okay, let me just look at the diagram. I don't even want to read it. I don't even know why. I feel like these diagrams are a little unnecessary, and like even if they felt it was necessary, they could have just injected the diagram instead of having this messy code, really. Anyways, comparing cards. Suppose we create a second card object with the same suit and rank. If we use the equals equals operator to compare them, it checks whether queen and queen 2 refer to the same object, which they do not, because they were instantiated separately. They don't, so it returns false. We can change this behavior by defining the EQ method. We talked about this already. EQ takes two card objects as parameters and returns true if they have the same suit and rank. So queen and queen 2 now is equal to each other, but also remember that they're equivalent but not identical, meaning queen equals queen, oh my god, I can't spell, is true, as we just saw, but queen 2 is false, right? Because they're different objects. As a second test, let's create a card with the same suit and a different rank. We can confirm that queen and 6 are not equivalent. 6 equals card 1 comma 6, print 6. Right. We can confirm that queen and 6 are not equivalent, because duh, they're not. If we use not equals operator, Python invokes a special method called NE if it exists. Otherwise, it takes EQ and inverts the result. So if EQ returns true, the result of the not equals operator is false. So, okay. This is good to know. I did not know that NE would just work out of the box like that, though it kind of is good that it does because it makes no sense that it wouldn't. Queen not equals queen 2, queen not equals 6. Now suppose we want to compare the two cards to see which is bigger. If we use one of the regional operators, we get a type error. Less than not supported between instances of card and card. To change the behavior of the less than operator, we can define a special method called LT, which is short for less than. For the sake of this example, let's assume that suit is more important than rank, so all spades outrank all hearts, blah, blah, blah. Def to tuple, which returns the suit and the rank as a tuple. And you can write this with less than. Okay, I see what's happening. So they're just taking this logic of like, oh, let's pretend the suits matter in terms of ranking cards, which they don't, to showcase that we can, return it as a tuple and then use that in the LT or less than function. With that working, I'm assuming I'm assuming it will invert the less than operator, the less than, not operator, less than magic function, just like it did with EQ, and that is indeed the case. It works queen greater than queen 2, and if you use the greater than operator, it invokes a special method called GT. Oh my god. Anyways, wait, this is not making much sense to me. Why is queen less than queen 2 and queen greater than queen 2 both false? Sorry about that. So why is queen less than queen? Let me just make sure there's no funkiness from runtime. Restart session, yes, and let's just run all above. Runtime, run before. Queen greater than. Why is queen less than queen 2 and queen greater than queen 2 both false? Oh, I think that's because queen and queen 2 are both equivalent. Right? Yeah, queen and queen 2 is equivalent. There you go. Yeah. So that's why less than compares the first element from each tuple comparison, compares the first element from each tuple, which represents the suits. If they are the same, it compares the second elements, which represents the ranks. Now, if we use less than operator, it invokes the LT method, 6 less than queen, true. If you use the greater than operator, it invokes a special method called GT if it exists. Otherwise, it invokes LT with the arguments in the opposite order. Okay. That makes sense. Yeah, that makes sense. You just flip the ordering of the less than and the greater than, and it gives you the same result. Right. Okay, good. I'm actually glad that my initial logic doesn't make sense, that it just inverts the response, like with EQ and NE. And that's good because, well, these two, queen less than queen 2 and queen greater than queen 2, actually proves why it's good, because, in this case, they are equal to each other. So if they are equal or equivalent, then both less than and greater than would be false. So that's an appropriate thing. Finally, if we use the less than equal operator, it involves a special method called LE. So boom, again, we're just doing the same stuff again and again now. If we use the greater than equals operator, uses GE if it exists. Otherwise, it invokes LE with arguments in the opposite order. So it's kind of weird to do the ranks thing and do the tuples thing, but what I think they're really trying to do is just showcase all of these dunder functions that are super helpful and super useful. As we have defined them, these methods are complete in the sense that we can compare any two card objects, and consistent in the sense that results from different operators don't contradict each other. With these two properties, we can say that card objects are totally ordered, and that means, as we'll see soon, that they can be stored. Sorry, I got distracted, boys. I don't know, I feel like I'm coming down with some sort of something. There's a really bad itch in between my fingers. Could be fungal, maybe. I don't know. We'll see. Decks. Now that we have objects that represent cards, let's define objects that represent decks. The following is a class definition for a deck. To create a list that contains the 52 cards in the starter deck, we'll use the following static method. Def make cards for suit and range 4, for rank and range 2, 15. Card equals card, suit, rank. Card starter, pen, cards. In make cards, the outer loop enumerates the suits from 0 to 3. The inner loop enumerates the ranks from 2 to 14, where 14 represents an ace that outranks a king. Each iteration creates a new card with the current suit and rank and appends it to cards. Here's how we make a list of cards and a deck object that contains it. Boom, boom. Deck equals deck cards. Class decks, self-style cards. Oh, I see. So they have this as a static method, which I'm so surprised. Like, because normally if you do a static method, you need to define the at static method decorator. But I'm guessing that's something special for this. Let me look this up. The add method 2. Command used in Jupyter notebooks, particularly within context of okay. Yeah, so it's weird that, let me see if I can print class, print deck. Vars dunder module, dunder init, dunder dict, dunder weakref, make cards function, dunder main dot make cards. Static method. Yeah, that's what I thought. I'm having a bit of a major malfunction here. I'm gonna test something. Okay. How to define static methods in Python. But what I'm not understanding Hmm. I'm just confused because every time I've seen static methods, like the one over here, usually I have to mention that it's a static method using the decorator, but not having to do that here, and I don't quite understand why that's the case. Um, I'm just gonna test this out in like my playground here. Let me just copy this. Class deck. Okay, let me also get the cards. Okay. Okay. So deck dot make cards. Instance method should take a self parameter by Pylance. Well, yeah, it definitely should. Print. Let's check it right here in the terminal because I'm lazy. uv run pg dot py. Oh, it does work. A. And if I don't pass this on, okay. Is this something that changed? I feel like this is something that's changed. Do I not need static method decorator anymore? Yeah, this is actually a really good function. Ah, okay. I see. I see now. I see. So basically, if you call the method from the class, if you call the method from the class, the instance doesn't pass to itself, right? So it won't. It's fine. Um, but if Mom's having a party. My mother just suddenly started playing a bunch of music. Sounds like 70s disco music. It's kind of fun. And now my wife is dancing to it. You wanna go show mom your dance? I think she would like it. Oh, okay. Anyways, it's still a static method, even if it's called from an instance yourself. So let's test that out. Deck. Let's do that, and then let's print dex.make cards. Yeah. Huh? Oh. Let's pretend it doesn't need that. And say pass. Yeah. Wait, what? This doesn't make sense. Oh, this is not making sense. Why is this happening? Dex equals a class of deck. And I'm still able to call it without... Oh. There you go. Now let me do this. Yeah, there you go. Yeah, dex.make. Yeah, okay. So basically, because I had this here, and remember, self is not like a reserved keyword or anything like that. It's not protected by Python in that way. So when I just passed A is just interpreted as self, as in aka the variable that contains the instance that calls it, right? So yeah, so you do still need to use the add static method decorator. It's just that you don't need it if you're calling it from the class itself, right? And so yeah, that makes sense. It's still a static method even if it's called from an instance via self, right? So regardless of whether you call it from an instance or not, it's going to remain a static method. So there's a video about class methods and static methods that I am tempted to watch. I will open it and maybe I'll watch it some other day. How long is it? Oh, it's only 15 minutes.
Hey everybody, how's it going? In our last video, we looked.
Who the hell is this Corey Schaefer guy?
Hey everybody, how's it?
Oh Jesus! Welcome to my channel. This is my channel focused on tutorial and walkthroughs. Async IO, complete guide to async IO. Visually explained. I'm gonna subscribe to this guy because I do actually want to watch this video about async IO. I might watch that someday in the future. I'm gonna just say that. Why I'm switching to UV? I completely agree. UV is the best, and everyone who's using Python should be using it. Python pathlib versus os.path. There's actually quite a lot of good videos here that I actually am curious about getting into. Anyways, so Corey Schaefer seems like a cool guy. Let's continue on. Why don't you go to her? You know she'd like it. Okay. Anyways, I'm just getting distracted with my wife and my mom.
What am I doing to get to distract you? I'm not even giving you a...
Alright guys, we were just gonna continue on with this. Anyways, as we just discovered, like, so when he's saying over here that he's using a static method, it's technically, in a sense, it's true, but it's not really true. So I wouldn't call it that per se, but that's not a big deal. It's okay. We tested out and we figured out why we use the static method decorator. We know then that it will remain a static method whether or not we call it from the class or from the instance of the class. Okay. Scrolling down, we solve this. Dex make cards, blah blah blah. I'm just gonna comment that out. Vars deck. In make cards, the outer loop enumerates suits from 0 to 3. Vars deck. Why did... Oh, that was me just testing for myself, I think. In make cards, the outer loop enumerates from the suit 0 to 3. The inner loop enumerates from ranks 2 to 14, where 14 represents ace, an ace that outranks a king. Each iteration creates a new card with the current suit and rank and appends it to cards. Here's how we make a list of cards and a deck object that contains it. Boom, boom. We already did that. Contains 52 cards as intended. Here's the Dunderster method for the deck. Res equals for card and self-dot cards, res dot append, start card, return, /n, join res. Yeah, so basically, I'm honestly not even going to go through this code. This method demonstrates an efficient way to accumulate a large string, building a list of strings, and then using the string method. We'll test this method with a deck that only contains 2 cards. Small deck, Queen of Diamonds, 6 of Diamonds. When Jupiter displays a string, it shows the representational form of string, which represents a new line with the sequence /n. However, if you print the result, Jupiter shows the printable form of string, which prints the new line as white space. Yeah, so that's the difference between a string and a string literal, basically. So the cards appear on separate lines. Add, remove, shuffle, and sort. To deal cards, we would like to add a method that removes a card from the deck and returns it. The list method pop provides a convenient way to do that. Here's how we use it. I'm not gonna... one thing that I think is really good for people who are reading this book is that they do spend time like reiterating and reusing things that we've learned up to this point. But for me, it's kind of irritating because I'm looking at this code. I'm like, oh, this is so arbitrary, and we're only doing it to showcase this thing that we learned a couple of chapters ago. It's not getting to the core concepts. As an example, we can put the card we just popped. Shuffle the deck. We can use the random module. Def shuffle self, random.shuffle self-talk cards. If you shuffle the deck and print the first few cards, you can see that they are in no apparent order. Sort the cards, we can use the list method sort, which sorts the elements in place, that is, modifies the list rather than creating a new list. When we invoke sort, it uses the LT method to compare cards. If we print the first few cards, we can confirm that they are in increasing order. In this example, blah, 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 parents and children. Inheritance is the ability to define a new class that is a modified version of an existing class. As an example, let's say we want a class. Okay, so now we're finally getting to real inheritance. As an example, let's say we want a class to represent a hand that is cards held by one player. A hand is similar to a deck. Both are made up of a collection of cards and both require operations like adding and removing cards. A hand is also different from a deck. There are operations we want for hands that don't make sense for a deck. For example, in poker, we might compare 2 hands to see which one wins. In bridge, we might compute a score for a hand in order to make a bid. This relationship between classes, where one is a specialized version of another, lends itself to inheritance. So this is what I was saying, right? Deck, the deck class, already has most of the stuff this hand class that they're about to get into is going to use. So it just inherits it and then adds a few more functions to make it specialized for the task it's needed for, right? That's the power of inheritance. Is like it stops it doesn't, it makes it so that you don't have to write the same code over and over again, which is more error prone if you're just writing the same thing again and again. And it just makes it succinct and naturally organized, I think. There's also a way to overload methods. So for example, if you take if you did inherit a function, but you don't want to use that version of the function, you can just create another function with the same function name, and as long as you're using the child class, it will be the child class's version of that method that will be used and not the parents, right? So that's what is known as overloading. Anyways, class hand. This definition indicates that hand inherits from deck. So if you want to inherit, you just put class, the name of the class, and then in parentheses write the name, put down the name of the class that you want to inherit from. It's as simple as that. Everything else pretty much follows from there. There's another thing about super, but I'm not gonna get into that. It's basically something you want to do when you're doing a mix of, okay, I'm mostly using the same function as what was defined earlier, but then I want to add just a little bit of extra stuff to that same function. So instead of rewriting and copy pasting the whole function, you can use super, which would call the parent class's function, basically. So I don't even know if they're going to get into that. I don't want to talk about it, but you can look it up if you want. Super function, it's literally called super, super. This version of init takes an optional string as parameter and always starts with an empty list of cards. When we create a hand, Python invokes this method, not the one in the deck, which we can confirm by checking that the result has a label attribute. Boom, boom. Let me just do that, then that real quickly. Player one. What is the label? Oh, okay. To deal a card, we can use take card to remove a card from a deck and put card to add the card to a hand. Hand object has no attribute put card. Okay. Okay, I don't know what he's talking about, put card and take card. I don't think those functions are defined. Are they? I'm gonna check the parent. Honestly, I don't care. Point is, you would need to write these functions, put card and take card. I'm not getting into that. Let's encapsulate this code in a deck method called move cards. This method is polymorphic, that is, it works with more than one type. Self and other can be either a hand or a deck, so we can use this method to deal a card from a deck to a hand, from one hand to another, or from a hand back to a deck. Okay. Works with more than one type. Self and other can be either a hand or a deck, so we can use this method. Okay, yeah, so that is polymorphism in action, I guess. And it makes sense. It makes sense that it's polymorphic. I feel like it's still slightly conceptual, but whatever. Anyways, I'm not even getting into this. When a new class inherits from an existing one, the existing one is called the parent and the new class is called the child. In general, instances of the child class should have all the attributes of the parent class. The new class is called the child. In general, the child class should have all the methods of the parent class, but it can have additional methods. If a child class overrides a method from a parent class, the new method should take the same parameters and return a compatible result. This set of rules is called the Liskov substitution principle. When a new class inherits from an existing one, the existing one is the parent and the new class is a child. Instances of the child class have all of the attributes of the parent class, but they can have additional attributes. The child class should have all of the methods of the parent class, but it can have additional methods. If a child class overrides a method from the parent class, the new method should take the same parameters and return a compatible result. Yeah. If I'm correct, none of this is specifically enforced by Python. I mean, the third one in particular. The first one and the second one, yeah, obviously, anytime you have a child class, you will have access to all the original functions and methods. And obviously you can define additional methods or additional attributes. But regarding overriding a class, um, saying that the new method should take the same parameters and return a compatible result, I don't think that is actually enforced by Python itself, right? Like you can just have a child class override a method and then take in completely different arguments and give a completely different type of result. But I would not recommend it because that's just hell to deal with, right? If you really want to do something like that, like a slightly different return value is okay, right? Like if it's like an integer in the parent and it's a float in the child, or vice versa, that's okay, like, right? Like the return value is something you can play around with, but the inputs, man, if you mess around with those, it becomes very, very difficult and confusing. And actually, I think in Python, if you define the same function twice and give it a different set of arguments, they're considered different function objects. I am not sure about that, honestly, though. So I will not confirm or deny that. Set of rules called Liskov substitution principle. If you follow these rules, any function or method designed to work with an instance of a parent class like deck will also work with instances of a child class like hand. If you violate these rules, your code will collapse like a house of cards. Sorry. Specialization. Let's make a class called Bridge Hand that represents a hand in Bridge, a widely played card game. We'll inherit from hand and add a new method, high card point count, that evaluates a hand using a high card point method, which adds up points for the high cards in the hand. Here's the class definition. That contains as a class variable a dictionary that maps from card names to their pound values. Okay. Given the rank of a card like 12, we can use card rank names to get the string representation of the rank and then use HCP_dict to get its score. What the hell? HCP_dict, there you go. High card points. Following methods loops through the cards in Bridge Hand and adds up their scores. Here's that method. Cards equals deck.make cards, deck equals deck cards. Random.seed3, that's just setting the seed. It's just code stuff at this point. Yeah, it's just basic code. So this is just like an example of inheritance, right? It's like, oh, okay, we created hand, we can create an even more specific inherited class for a more specific use case of the class hand, right? So it's pretty straightforward.
Babe,
Yeah.
can you come and get me after 15 minutes?
No, babe, if you're going to bed, then go to bed.
I'm at work. I just need a 15 minutes break.
Okay. So my wife is going to bed and she has asked me to wake her up in 15 minutes, and I don't like waking her up from sleep. I don't like waking up anyone from sleep. Your sleep is important. Don't disturb people while they're sleeping. Seriously. Unless there is a serious need to do it, don't disturb someone's sleep. It's like, I actually think it's considered torture under the Geneva Convention if you disallow someone from sleeping. Anyways, debugging. Inheritance is a useful feature. Some programs that would be repetitive without inheritance can be written more concisely with it. Also, inheritance can facilitate code reuse since you can customize the behavior of a parent class without having to modify it. In some cases, the inheritance structure reflects the natural structure of the problem, which makes the design easier to understand. On the other hand, inheritance can make programs difficult to read. When a method is invoked, it is sometimes not clear where to find its definition. The relevant code may be spread across several modules, which is very true. That is actually a genuine problem. Anytime you're unsure about the flow of execution through your program, simplest solution is to add print statements at the beginning of the relevant methods. If deck.shuffle prints a message that says something like running deck.shuffle, then as the program runs, it traces the flow of execution. As an alternative, you could use the following function, which takes an object and a method name as a string and returns the class that provides the definition of the function. The string returns the class that provides the definitions of them. Find defining class, hand, comma, shuffle. Okay, maybe I'm a bit tired and I'm unable to fully grasp what they're saying, but it's not making much sense to me. Glossary, inheritance, ask a virtual assistant, exercises, more classes and inheritance stuff, I'm guessing, yeah. Smith hash rate. This is just some basic programming. Not basic. I wouldn't. I've been really mean saying basic because some of these are, I wouldn't say hard, but it's not like I would just be like, I can do it instantly, right? I'll have to look at them, understand them, think about them, do them. It's just that they're kind of arbitrary, and I don't want to do that, right? Especially because I'm not in the phase. I'm not in a phase where I need to practice this stuff per se. But if you are, you definitely should. I'm just gonna call it. I'm gonna call this chapter. This is and this video. It's done. Next one is chapter 18, which is Python extras. 18 and 19 I'll just do together. I think they should be both really quick. I don't know what's in these chapters, but I'm sure it'll be pretty quick. Yeah, so I'll see you in the next one, boys. Have a great one.